A processor uses two-level paging. So see, this question is given in GATE 2003 CS paper. You can look at that question. What I did is I just edited some parts out which are because the question is too big and I cannot write it completely on the board. So I have written the important things and I edited it out. I just changed the wording, that's it. I mean, whatever they could have written it compactly, they have expanded it. I just changed the wording, but the question is as it is. I'll explain it here. You please read it once, okay? And moreover, this question is a linked question, which means not linked question, common data question. The data, using this data, they have asked two questions. I'm going to solve one question first, and after this solving this, I'll solve immediately the next question also, okay? So let's see the data. They are saying that a processor uses two-level paging. So two-level paging means one level page table, second level page table, and then the process, right? And then virtual address equal to physical address equal to 32 bits. They are saying that the addresses are 32 bits, either the virtual address and the physical address, both of them, and it is byte addressable. So byte addressable means that whenever the why should they say it is byte addressable or word addressable and size of the word is whenever they talk about the addresses in bits, then the address space is going to be 2 power those many bits. If the virtual address is 32 bits, then the address space is going to be 2 power 32, and now that is the address space, which means number of addresses. Then what is the size of the unit each one is addressing? That depends on what kind of addressable it is. If it is byte addressable, then the size is 2 power 32 bytes, right? If it is word addressable and if the word is 2 bytes, then the size is 2 power 32 into 2 bytes, right? Or 2 power 32 words, and then you have to convert the words into next thing bytes. And next one is virtual address is divided like this. So virtual address is divided into three parts. First one is 10 bits, 10 bits and 12 bits. They are saying that the first 10 bits are used to index into the outer level page table. Therefore, how many entries are there in the outer level page table? 2 power 10 entries are there, right? And the second 10 bits are used to index into the inner level page table, which means in the inner level page table, in each page, see, outer level page table has to be only one page, otherwise we will go for one more level of page table. Always remember, outermost level will always contain one page. Either it will be less than or equal to less than one page, or it will be exactly one page, but it cannot cross one page size, right? And now this one is this 10 indicates that the inner level page table has 2 power 10 entries. And then finally this 12 indicates that the size of the page, a page is able to hold 2 power 12 bytes. Therefore, even though they didn't say anything about the page size, you can guess the page size here. So how much is page size? 2 power 12 bytes. How? Because the offset bits are 12 bits. And then they are saying that page table entry is 4 bytes. Anyway, you could guess it. So if the page size is 4 KB and the number of entries in the page is 1 KB, you can easily guess what the page table entry size is. That information is redundant. And next thing is TLB has a hit rate of 96%. So why is TLB used? As usual, in order to find out the most frequently used page table entries. If a entry is most frequently used, we can find it out, right? And cache has hit rate of 90%, which means if you are having a cache memory, then the hit rate is 90%. Okay, so what is cache and what is TLB? Both are actually cache memory only, but the main difference is TLB is normally used to save the page table entries, and cache is normally used to save the words from the process, or the bytes or the data from the process, right? So now the question is, we have two things. One is TLB, which is used to save the page table entries, and other is cache, which is used to save the frequently used part of the process. And then they are asking, main memory access time is 10 nanoseconds. This is given, right? Main memory access time is 10 nanoseconds. So if we don't find an entry either in TLB or in cache, then we are going to go into the main memory and it is going to take 10 nanoseconds, and cache access time is 1 nanosecond. So cache obviously is faster, and TLB access time is 1 nanosecond. Then the question is, assuming no page fault, which means assume that there is no page fault which has happened. So in case if there is page fault, then again you might have to talk about the page fault service time also, right? Assuming that there is no page fault, there are no page faults at all, whenever you try to refer to something in the main memory will always give you that. That is the meaning of no page fault. If there is page fault, what does it mean? Whenever you try to refer to main memory for something, even main memory might not have it, and therefore you might have to go to the secondary memory and get it. That is called page fault service. If there is no page fault, your end of searching or your searching should end at main memory. So where are you going to search? Initially TLB and then the main memory for the page table entries. Similarly, where are you going to search the word of the process? Initially cache and then the main memory. Okay, I'll take the diagram and explain you. Don't worry about that. Now assume that there are no page faults. The average time taken to access a virtual address is approximately, so to the nearest 0.5 nanoseconds. So they are asking about the average access time to access any virtual address, which means in order to get a byte from the main memory, how much time is required on average, which is nothing but they are talking about this average access time, right? Effective memory access time, that is also called. Okay, and now they are saying that answer is not exactly required. You can give the approximate answer, which should be near to the 0.5 nanoseconds, which means whatever answer you get, it could be around 0.5 nanoseconds around the given options. So if you fall anything which is closer to the options, you can go for it, which means let us say you got some answer and it is at a distance less than 0.5 nanoseconds from the given options, then you can go for it. That is what they are saying. Okay, I'll explain the question why here. Now whenever CPU generates a logical address, it contains two parts. One is page number and other is page offset. You already know it, right? And now using the page number, we are supposed to get into the TLB memory, right? TLB. If it is present in TLB, then we can directly get the frame number, right? And then using this page offset, you can get the physical address. Fine. If it is not present in TLB, then we are supposed to go into the main memory and access the page table, right? Main memory and access the page table. But in this case, two page tables are there. Therefore, you might have to access the main memory two times. So that is about how to convert the virtual address to physical address. So initially, whenever CPU generates the virtual address, you have to convert it to physical address first, right? Just to convert it to physical address, what are the important things here? One is TLB. If it is present in TLB, we can directly get it. If it is not present in TLB, you are going to get into the main memory, and from main memory, we are going to access main memory two times and finally convert the virtual address to physical address space, right? And now once we get the physical address, right, then what happens is, again, CPU is going to have something called as cache. So there are chances that the word which you are looking for of the process, the byte of the process, might be present in cache. In case if it is present in cache, you can directly give it to the CPU, right? In case if it is not present in cache, again you have to go into the main memory, right? Therefore, there are two parts here. One part is converting virtual address to physical address. Second thing is, after getting the physical address, getting the word from the main memory. So these two times have to be estimated. Are following it? Now CPU is going to generate virtual address. First we have to convert it into a physical address. For that, TLB is going to be useful. In case if TLB it is not containing it, we have to go to the main memory, and there we have to do it two times because it is a two-level page table. And the second thing is, once we get the physical address, we have to go to the main memory and get the word. But cache helps there. So I didn't say anything about cache as of now, but in CO we are going to discuss about cache. But just remember it here. Whenever we have cache included, what I mean to say is this way. If you have cache involved, before going into the main memory for searching for a physical address, see, virtual address will be searched initially in the TLB, physical address will be searched initially in the cache. So before going to the main memory, for searching for the given word, you search inside the cache. Cache is going to be faster compared to the main memory. Got it? Okay. So now let's solve this. Effective memory access time is what they are asking, right? Or that is also called as average time taken to access a virtual address. Now let's compute this. Effective memory access time, it is of it comprises of two types. One is if you have to access a virtual address First we have to, okay, instead of calling it as effective memory access time, that will be confusing. Effective, okay, so let's take the same parameter, same thing, average time taken to access virtual address. Average time taken to access virtual address, that equal to how much time will it take. It actually comprises of two parts. One part is, first you convert the virtual address to physical address, and then you go to the main memory and get the word, right? So it contains of two parts. Virtual address has to be converted to physical address, first thing, and then it is going to take some time, and then fetch the word, or byte in this case because it is byte addressable, fetch the word from process, right? That is nothing but the main memory, right? So first you convert the virtual address to physical address and take the physical address and then get it from the main memory, right? So here, in order to convert virtual address to physical address, we are going to take the help from TLB, and here, in order to fetch the word from the main memory, we are going to first look into the cache. If in case it is not present in the cache, then we will go into the main memory, right? So how can we do it? So in order to convert the virtual address to physical address, first look into the TLB. If it is not present in TLB, then we will go into the main memory, right? So how can you write it? So I think we have already seen a lot about TLB. I am directly writing it. So in order to find it out, one thing is you have to search in the TLB whether it is present in TLB or not. First you have to search it, and after searching it, in case if it is present, we stop it here. In case if it is not present, then that is called as miss, right? So TLB miss. So here it is given as TLB hit. If TLB hit is P, then TLB miss is 1 minus P, right? In case if it is a miss in TLB, then what should we do is, we should go into the main memory and get the page table entry. Now here the main memory is containing two levels, right? When there are two levels of pages, I might have to search in two levels, right? So let me write it as K. K is the number of levels which are used in the page table, K into main memory access time, because I have to access the main memory these many times. Are you understanding this? If it is present in TLB, it is T, right? In case if it is not present in TLB, there is a probability with which it is not present in TLB. Then for that one, I might have to do this extra work, K plus M. Anyway, T is always, this work is always going to be there. This extra work might be there sometimes. On average, we are going to get this time just to convert virtual address to physical address. And now once we convert the virtual address to physical address, then we have to fetch the word from the main memory, right? Now for this one, again the same thing we are going to do. We are going to search in the cache. Let us say C is the time taken to search in the cache. In case if it is not present in cache, which means if it is missing the cache, let us say PC is hit rate of cache and PT is hit rate of TLB, then PC 1 minus PC is miss rate of the cache. In case if it is not present in cache, then I am going to go and search it from the main memory. Got it? So this is the total time required. It is all logical. Don't try to by heart it. I think it will all be logical. Once you understand this, you can directly do it. Don't never by heart it. Okay, in case if you are used to it, I can't help it. Go ahead with that. What about this? TLB access time and cache access time both are 1. So in this case, TLB access time is 1 nanosecond plus what is the hit rate of the TLB? TLB hit rate is 96%. Then what is the TLB miss rate? 4%. 4% means 0.04. See, 4% is not 0.4. You might make a mistake there. 4% means 0.04 into K into M. So what is K? The number of levels. Number of levels is 2. And what is the main memory access time? Main memory access time is it given? Yes, it is given somewhere as 10 nanoseconds, right? 10 nanoseconds. This entire time is required to just get the page table entry. So once we get the page table entry, we can get the physical address. Now once we get the physical address, we have to get into the cache and see whether it is present there or not. In case if it is not present, we have to get into main memory and we have to get it, right? So now how much time is it going to take in order to look into the cache? C time, which is nothing but 1 nanosecond plus what is the miss rate of cache? So hit rate of cache is 90% and therefore what is miss rate of cache? 10%. 10% is 0.1, not 0.01. Okay, and whenever there is a miss in case, no, when you are searching for the physical address, we are searching for only one word and it is present at only one place. You need not search two times. Why am I writing two times here? Because it is two level caching, so two level paging, which means I might have to go to two different pages. That is why it is 2 into, but here it is just 1 into 10 nanoseconds, right? And now if you solve all this, you will get 3.8 nanoseconds is the answer, right? And now they are asking it, what is the close approximately which one do you want to pick, which is closer by 0.5. so obviously the answer which is closer to this is 4 nanoseconds. I don't know why they didn't give 3.8 and why they are asking close approximation. I don't know what is there in this. So anyway, 3.8 is the exact answer and the approximate option is 4 nanosecond. They are asking about approximate answer. Got it? So here there is a combination of TLB and the cache. You are lucky that they didn't combine this question along with the page fault also. In case if there is page fault, you guess what would have happened? In case if there is a page fault, right, then entire thing has to be changed, right? So why? Whenever you are searching for that page, that might not be present there. So here there might be a change, which means the memory access time might not be directly m. In this case, you might have to include that page fault rate. So what will come here? M plus p into, if I'm just telling you, if you are following it, follow it, otherwise leave it. Okay, see, in this case, if there is page fault, what happens is when you are searching for the required word, then the required word might not be directly present in the main memory. Then what happens is you might have to do m plus p is page fault rate into page fault time, right? Which means you might have to add m plus p into page fault. So if they had given it, but then they have clearly mentioned that there is no page fault. Got it? See, so here there are two levels of memory which are used. Later we shall see what it is. One is cache. In CO we shall see it. Other is memory, and other is secondary memory. It is main memory and secondary memory. First we'll search in C. If it is present in C, fine. If it is not present in C, we are going to get into main memory. If it is present in main memory, fine. If it is not present in main memory, we are going to get into secondary memory, right? That is why we get like this. Initially, we have to search in the cache. If it is present in cache, fine. If it is not present in cache, this is the probability, then we might have to incur extra cost, right? And then the extra cost will be, if it is present in main memory, it is fine. I'm just going to write it here. I don't want to confuse you, but it is very simple, and I know it is just an extension of the concept. If you want to learn it, fine, otherwise leave it. Okay, now in case if it is present in cache, okay. In case if it is not present in cache, we have to go to the main memory. In case if it is present in main memory, it is fine. If it is not present in main memory, right, then we have to incur extra cost. How much is that? 1 plus 1 minus, let us say, not 1 minus, let us say PF is the page fault rate. So in case if there is a page fault, I might have to incur extra cost of page service time. This is how we could solve it. Understood this? So what is the meaning of this? If it is present in cache, it is fine. In case if it is not present in cache, you might have to go and search in the main memory. And when you are searching in the main memory, in case it is present in main memory, it is fine. In case if it is not present in main memory, you might have to go and get from the secondary memory. That is why this extra cost is going to be required. Later in CO, we can see what are the various levels of memories and how to solve it. But then here in this question, they have given only two levels. One is cache and other is main memory. And whenever they didn't mention anything about why cache is used and why TLB used, always remember that TLB is used to save the page table and cache is used to save the the actual elements of the memory. I mean the process, the bytes of the process. Okay. Now there is one more linked question for this. I'll write that question and then solve it. Fine. Now let's try to solve the second question of this. For the same data, they are saying that suppose a process has the following pages in virtual address space. They are saying that a process is having these pages, two contiguous code pages starting at so and so address and two contiguous data pages starting at so and so address and a stack page starting at so and so address, the amount of memory required for storing page tables of this process is. So now they are saying that so they actually didn't say anything about the page table size. So okay, before solving this, why don't we solve the other one? In a sense, how is it organized is, one thing is they didn't say anything about the page size, but they said that the least significant 12 bits in the virtual address is going to act as the offset into the page. So if the page offset is containing 12 bits, then what will be the size of the page? 2 power 12 addressable units, and it is byte addressable. Therefore, the size of this memory at the page is 2 power 12, which is 4 KB. So one thing is for sure, the size of one page is 4 KB. That is what we found out. And next what happens is the page table. Now if you look at it, the virtual address page address is 32 and the page offset is 12 bits. Therefore, the number of entries or the number of pages is 2 power 20, which means 1 million pages are present, and each page table entry size is 4. Therefore, 4 MB is the size of the page table. So 4 MB is the size of the page table, and the page size is 4 KB. Therefore, it cannot fit in one page. Therefore, we are going for two levels of paging. And when we do it into two levels of paging, the outermost page table indexing into the outermost page table contains 10 bits, and indexing into the innermost page table, one page contains 10 bits. Therefore, what is the size of the outermost page table? It contains 2 power 10 entries, and size of each entry is 4 bytes. Therefore, 2 power 10 into 4, which is 4 KB. So outermost page table is going to fit in one page. Fine. So in order to run this process, always the outermost page table should be in the main memory, right? So what can you say? One page is definitely required, which requires 4 KB in order to put the outermost page table. And now we should decide how many pages in the inner page table are required, right? And every page in the inner page table size is 4 KB. Now depending on the number of pages in the inner page table required, we can find out how many, right? So what I mean to say is, it is having two levels of page tables. This is the outermost page table and this is the innermost page table, right? Outermost page table is just one small that it can fit in one page, and the innermost page table is again divided into many pages, right? And now depending on which pages we need, let us say if we need this page and this page and this page, this is always this has to be present. And in case if you require 3 pages of the innermost page table, then what is the total space required for the page tables? Then it is 4 into page size. Each page is going to contain 4 KB, right? And at any point I need the outermost page table. Therefore 4 KB is already required, and along with that I'll try to see what are the pages which are referred in the innermost page table, right? So how can we know what are the pages which are referred in the innermost page table? That depends on how many entries we are referring. Okay, I'll just tell you that. Okay, fine. So now what is that they are trying to say is, anyway this information is now irrelevant. I'm just going to erase it. I'll just solve it here. So now what is that they are asking is, if the process requires 5 pages starting at various locations, then what is the size of the page table which has to be present in the main memory, or how much memory is dedicated to the page tables overall? That is what they are asking. If you see this, they are saying that two pages are starting at the address 0x1 2 3 4 5 6 7 8, 32 bits. 0x means hexadecimal, and each number here is actually equal to 4 bits. So 8 numbers are there. 8 into 4 is 32, right? And now we know that the least significant 12 bits, is nothing but 3 digits here, right? This one represents the page offset. So if two pages are starting from this location, can you tell me what are the addresses present in each page? One page contains from this address to 0x0000F, right? So this is the range of one page, and the second page is going to start from 0x00001 1 2 3. Why? Because the address which is after this address is this one. Therefore the second page starts from this and ends at 0x 1 2 3 4 5 f f f, right? So these are the two pages, right? In fact, this is page number of one page and this is the page number of the other page, right? So how many bits are they containing? It is 20 bits and it is 20 bits. Now these 20 bits are again divided into two parts. One is indexed into the outer page table and other is indexed into the inner page table, right? So now what I mean to say is, if this one indexed into the outer page table is all zeros. So what are the most significant 10 bits? The most significant 10 bits are 0 0 and 2 zeros from this, all zeros, all zeros. Therefore both these pages are going to refer to the same entry in the outermost page table. Therefore when they refer to the same entry, they will be pointing to the same page in the innermost page table. So both these pages, if they have to be accessed, they have to be referring to the same page of the inner page table. Already outer page table one page is present. Now from the inner page table we might need one page. Why? Because two pages are going to refer to that page table entry. Got it? So from the inner page table, because of these two pages, I need one page, right? And the next one is, they are saying that two data pages are starting at address 0, that one. So again two pages are going to start at the address 0x, which means hexadecimal 004 1 2 3 4 5, right? So then what happens is, first page is going to start from here and end at 004 0 0 f f f, and the second one is going to start at 0x 004 01 and then 000 and then 0x 004 01 f f f by all ones. It is going to start with all zeros in the offset and end at all ones, right? Now if you look at these two pages, see, this is the page number of the first page and second page number, right? These two pages, they too have the same most significant 10 bits. The most significant 10 bits are again, if you watch it, the most significant 10 bits, if you can write this one, it is going to be 0 0 0 004. This contains most significant 10 bits, right? If you write it 1 2 3 4 5 6 7 8, and what is 4 is 0 1 00, right? So this is the most significant 10 bits, 1 2 3 4 5 6 7 8 9 10, right? And now these most significant 10 bits are going to be used in order to index into the outermost page table and refer to one of the pages of innermost table. So if you watch it, here we are referring to 0 0 0 0 0 0 0 0 0 0. This is the index which we have used in order to refer to these two pages from the outermost page table. And coming to the next, these two pages, this is the index which we are going to use into the outermost page table. Therefore this number is going to point to one page of the inner page table and this number is going to point to the other page, which means for the first two pages we are going to refer to one page in the inner page table, and for the next two page tables we are going to refer to some other page. The reason is both are different entries, right? Therefore these two combinedly require one more page. So these two combinedly require one page in the innermost page table whose size is 4 KB, and these two combinedly require one page in the innermost page table whose size is 4 KB. And anyway we have the outermost page table whose size is 4 KB, right? And along with that we have one more reference. See, we have one more page which is starting at 0x 1 2 3 4 5 1 2 3. This is the page number, right? Now if you look at this only page, this is starting with here, the most significant 10 bits are all ones, 1 2 3 4 5 6 7 8 9 10. So this is going to be used as the index into the outermost page table, which will refer to a completely different entry, right? Therefore these two pages are referring to one entry and these two pages are referring to one entry, and this page is referring to a completely different entry in the outermost page table. Therefore these three entries are going to refer to three different entries in the outermost page table which are leading to requirement of 3 pages, isn't it? So from innermost page table, so this one requires one page of size 4 KB, this one requires one page of size 4 KB, these two, and this one requires finally one page of size 4 KB. And anyway, outermost page table should occupy one page, right? Therefore one page, totally 4 pages are required. Are you understanding this? Because outermost page table has to always be there, and these 2 pages are require one particular page in the innermost page table, and whose entry is pointed by all zeros in the outermost page table, and these 2 pages of the process requires one page of the innermost page table, and whose index is given by the address 00 followed by this one, right? And then this one is again referring to a different index, right? Therefore 3 pages of innermost page table and one page of the outer page table is required, and a total of 4 pages are required. If size of each page is 4 KB, how do I know that size of each page is 4 KB? Because page offset is 12 bits, isn't it? If size of each page is 4 KB, then I need 4 pages. Therefore this is the answer. Okay, 16 KB is the answer. Fine.